Okay, good morning, everyone. This morning, Hunter Spink will reveal the quasisymmetric electrode.
Thank you for inviting me here. It's lovely to stay at the IAS and visit with a lot of you. Today I want to do the follow-up talk to Vasu's talk, where we take these quasi-symmetric divided difference operations and give it some algebraic geometry. And this work is joined not only with Vasu Tewari and Philippe Nadeau, where we developed the combinatorial side of things, but also Nantel Bergeron and Lucas Gagnon. And we believe now we've found the true geometric picture for how you should think about quasi-symmetric polynomials now and hopefully forever into the future. It's not going to change anymore. Okay, so of course the overarching question is how do we put U in front of Z? All right, so let me just tell you, before I tell you what the geometric story ends up being, that, you know, we can do a bunch of different things. We can do it in type A, we can do it in type B, we can do a K-theory version. And what it looks like is once you have the right geometric model for quasi-symmetrics, there really is no actual obstruction to taking like a bulldozer through the literature and just taking every single paper and just like converting it into quasi-symmetrics in a rather systematic way. And all of the combinatorics ends up being very interesting and combinatorially positive, unlike Schubert calculus usually is, which is quite a nice feature. Okay, but I want to start by reminding people, you ideally, about how Schubert calculus comes to be. So how can we come up with Schubert calculus? With Schubert. And I want to say from first principles. So let's say I don't know even that Schubert cells are an interesting thing to look at. How do I connect polynomials with some operations on them? So I want to connect polynomials with operations like del I. I want to connect them to geometric. Okay, so what is this del I? So I'm going to motivate how the quasi-symmetric flag variety is going to be built by showing you how the usual flag variety could be constructed with all of its lovely Schubert cells. So here del I is this operation that takes a polynomial. So this is in polynomials and x1, xn, and it spits out polynomial minus that same polynomial where I've swapped xi and xi plus 1. Plus 1. You divide by xi minus xi plus 1. So this operation satisfies a bunch of remarkable relations. These, del I squared equals 0, del I del j equals del j del I, 1 minus j is at least 2, and del I plus 1, del I is equal to del I plus 1, del I plus 1. So if you just came up with this operation, you just thought this is a great symmetrizing operation I can do to polynomials, and you want to study it, you're like, okay, I can come up with these lovely algebraic relations that these operations satisfy, and this makes it intrinsically interesting to study del I and polynomials that interact nicely with it. So how do we come up with the geometry? How was this originally done? So I'm going to be a bit ahistoric. I'm going to start with the del I, and then we're going to produce from nowhere, we're going to spring up Schubert cycles. They're just going to appear. Okay, so how did they appear? The key is this fundamental result of Bernstein, Gelfand, and Gelfand. So much like Aval, Bergeron, and Bergeron, the paper was so good, he put his name on it twice from 75, where they describe an operation that's adjoint to del I in an appropriate sense. So to set this up, consider the flag variety. I'll just put this isn't, all this is going to be Aval, Bergeron, and Bergeron. Sorry, Bernstein, Gelfand, and Gelfand. So we're going to take the complete flag variety, which is GLN, the space of invertible matrices, modulo B, the upper triangular matrices. B, this matrices that look like this, which lies inside GLN. And the complete flag variety parametrizes flags of subspaces. So here, elements of this are in bijection with ways that I can describe a one-dimensional space inside a two-dimensional space inside an n-1 dimensional space inside C to the n. And what is this correspondence? It's actually very explicit. If I take a matrix M with its columns being V1, V2 through Vn, then this flag of subspaces, Vi, is just the span of the first I columns. And somehow the assignment from matrices to these subspaces that obviously are nested inside each other and increase, which matrices are equivalent to each other under this map that associates a matrix to this flag of subspaces. The answer is you can do column operations that add multiples of earlier columns to later columns, because that's not going to change this flag of subspaces. So you naturally get that B, these upper triangular matrices, are acting by column operations on the right of GLN. Okay, good. So that's just, warm up for what the flag variety is. Now, inside the flag variety, we have the following remarkable operation that I'm going to call pi I. Okay. So pi I is an operation that takes flags of subspaces and it forgets the ith subspace. Forgets the ith subspace. So this map pi I is actually a map from the flag variety to GLN mod a slightly bigger group called PI, the ith minimal parabolic subgroup, which looks like this. So PI looks almost exactly like B does, except there's one extra entry on the, there's one extra box on the diagonal. And what this one extra box is doing is it's saying that in addition to being able to do these column operations moving forward, you can also do a little bit of a cheeky thing, and you can take Vi plus 1, and you can add a multiple of it back onto Vi. So that one extra box off the diagonal is saying I'm allowed to go do a backwards column operation. With the forward column operations from the previous V's and this one extra backwards column operation from this next V, this completely obliterates the data of what Vi is within the span of the first I plus 1 vectors. So consequently, this map, the data that a matrix remembers in GLN mod PI is exactly these sequences of subspaces where we don't include the I subspace, the I plus 1 and Vn, where here now I should say that dim Vj is equal to J. Okay, geometrically we have this map that just forgets a subspace. Okay, so I have this map that forgets a subspace. And this unfortunately takes flags in the flag variety and turns it into these partial flags. So to get an object back in the flag variety, we want to be able to take things in here and pull them back to the flag variety. So here is the key operation. Pi I lower star. So what we're going to do is consider the following operation. This is what BGG considers. This is BGG. Consider this geometric operation. So this geometric operation takes cycles in the flag variety. So I would say it takes the homology of the flag variety, turns it into other homology classes in the flag variety. Concretely, what this map does is pi I lower star just means take the image, but if they're positive dimensional fibers, destroy it, but that's a minor technical point. And then pi upper star just says take the inverse image. So composing, forgetting the I flag, and then pulling back means you replace the I flag, replace this VI with all possible fillings between VI minus 1 and VI plus 1. Okay, so that's what this map is doing geometrically. And now, what is the significance of this map in relation to this operation del I? Well, BGG showed that under the natural pairing between cohomology and homology, so here we have homology of the flag variety, and cohomology of the flag variety to the integers. So under this natural pairing between homology and cohomology, this map pi I lower star, pi I upper star, pi I lower star is adjoint to del I. Okay, now what does it mean to be adjoint to del I? Well, the cohomology ring of the complete flag variety by a result of Burrell from the 50s says that the cohomology ring is given by polynomials in these variables x1 through xn, where here, for the people that know, xi is the first churn root of the dual of the vector bundle that you get, of the line bundle you get by quotienting the ith vector bundle ith line bundle associated to vi divided by the I minus first line bundle associated to vi, but that doesn't really matter. So it's polynomials modulo symmetric polynomials. So you quotient out by all polynomials in x1 through xn minus their constant term, where f is symmetric. So let me there we go. So this is the ring of symmetric coinvariants. So that means H star FLN is the symmetric coinvariants. And what it means for pi I upper star, pi I lower star to be adjoint to del I means that if I have any variety X and any cohomology class F, so here I'm denoting this pairing by angle brackets, then we can, if I put a del I, well, I'll say it in the forward direction. If I do pi I upper star, pi I lower star X, and I pair with the cohomology class F, then this is equal to the pairing of X with del I of F. So this gives you a way to build varieties whose degree maps naturally encode divided difference operations. Because if I use a sequence of these pi I upper star, pi lower star maps, I can apply a sequence of them to some fixed variety. And then this adjointness lets me move all of these geometric building operations to the other side on cohomology, where they become these algebraic divided difference operations. Okay, any questions so far? Okay. Great. So let's do the following. So I don't know what Schubert cycles are. Let's just take a point. So I take some point inside the flag variety. Let's actually take, for concreteness, the point corresponding to the identity matrix. Have to choose something. Okay, let's call this X sub X superscript id. Just a point. Okay, what do we know about the degree map on a point? Taking the degree of a cohomology class on a point is really dumb. You would take the constant term of your polynomial, because anything that's not degree 0 is too high degree to pair with the point and give you something non-zero. Okay, so step 1, point has nice degree map. Okay, so how do we now make a variety which has the magic property that it encodes sequences of dels followed by f0? Well, if I have so let's say I now have a sequence of let's say I have a sequence I1, I2, ik, and I want to write down something which has a nice degree map. I can try composing these building operations in reverse order. So pi ik upper star, pi ik lower star, pi ik minus 1 upper star, pi ik minus 1 lower star, pi I1 upper star, pi I1 lower star, x id. I can say, what is the degree of this monstrous variety? Let's call it xw, because why not? What is this degree map? Well, the adjointness tells us that I can move this over to the other side and produce a del ik. I can move this to the other side and produce a del ik minus 1, etc. in sequence. So what you get is, after applying all of those adjointnesses, you get the pairing of a point with del I1, del I2, del ik of f. And those relations, the braid relations, the Nilhecke relations, say that this is going to be a well-defined operation del w, provided that this is a reduced word decomposition. And then pairing with x id gives you the constant term of del w of f. Okay, so we now have this way of creating varieties whose degree map is exactly the constant term of apply a sequence of divided difference operations to f. And now, okay, coincidentally, it just happens to turn out that these things end up being these BWBs. But they didn't have to be, it was just random. So this is the other thing that BGG proved. I mean, I don't know. If I only care about algebraic combinatorics, do I really care what this process spits out? It's tough to say. Well, I care a little bit for some reasons, but okay. So this variety XW turns out to be XW is BWB closure. Okay. Now, there's some remarkable additional things that happen with this definition that makes it particularly nice. So one nice thing that happens is that the pi I lower star, pi I upper star, pi I lower star operations geometrically satisfy the nil-Hecke relations. Those nil-Hecke relations of del I on the nodes. So this is something that didn't have to happen, but turned out to happen here, and it was quite nice. That in theory, we're just acting on homology classes. I'm saying I can take a homology class, I can push it forward and pull it back, but maybe during this process, I also moved it and deformed it and did something. And then at the end, all you get is a homology class that might not geometrically be literally the result of applying these operations. But it turns out that these operations on the nose satisfy these relations. If you do it twice, it gives you 0, because the first time you do it, you saturate the fibers of this map. Then when you do it the second time, pushing forward kills anything with positive dimensional fibers. If I have two of these operations that are very far away, I forget the ith flag and then I forget the jth flag, and they're really far apart. Doesn't matter what order I try and do these fillings in, they're going to commute with each other. And then this last one where you forget the ith flag and you forget the ith plus first flag and you forget the ith flag. That's the same as forgetting the I plus first flag and then the I flag and the I plus first flag, because that basically gives you all ways of filling in everything between the ith and the I plus second flag. It's just describing this three-step process for just getting any random two intermediate flags into there. So they actually satisfy them on the nose. So this is a good geometric definition. This is like good not just as homology classes, but as cycles in the flag variety. It's also nice because the open parts of these xi, the relatively open parts of these xi's, these BWBs, are affine variety, are literally affine spaces. Concretely, what are these affine spaces? This is when you do Gauss-Jordan elimination and then you have a matrix with a bunch of 1s, 0s, and stars. Those stars are the coordinates of the affine space that BWB is representing. So they're literally isomorphic to affine space, so you get something called an affine paving. Which means that the flag variety, the whole flag variety, it turns out, is just built up out of these open BWBs. You just slap on these affine spaces that are glued in extraordinarily interesting ways. But they are just affine spaces, and you can glue it up. And what it means is that the homology of the flag variety actually has these XWs as an integral basis. So these XWs form an integral basis. Technically, to make it integral, the reason that you're able to do it integrally is some coincidence with the type A root system, and type B it's not. Bad things in type B, right? Good things in type B?
Completely general.
Great, okay, so integral basis, perfect. Didn't even need type A, but let's stick with type A. Type A. Okay. Okay, it doesn't matter. So, right, so we have the flag variety has this affine paving. And then the last thing is, so we said, okay, we've now shown that this nice basis that comes from an affine paving has these lovely degree maps on them. It's very easy to take the degree of cohomology classes on them in this sequential way. What's the last step of this puzzle? Well, that's provided by Lascaux and Schutz and Berger. Lascaux and Schutz and Berger from the same time, so 70s. They created a family of polynomials called the Schubert polynomials. So they're special polynomials. Schubert polynomials. Say how many variables they're in, because they actually satisfy a remarkable stability property. So they're polynomials, but I'm not saying how many variables they're in. And it has the property that that if I do this map del W S W prime, this is del W W prime. So they're special polynomials. Let's say they're homogeneous and they satisfy this property. And in fact, they're a unique family of polynomials. And to make it a theorem, I can't be talking about how nice these polynomials are. So there exists a unique family of polynomials called Schubert polynomials, indexed by permutations in S n. So here we can include S1 into S2 into here. So I can consider all of the symmetric groups on one footing. And these magic polynomials are dual to these degree operations. So the consequence of that is that from this resultant Bernstein, Gelfand, and Gelfand's result, we see that the Schubert cycles are Kronecker dual XW classes are what are called Kronecker dual to the Schubert polynomials, which also happen to form a basis of this H star n. So let me just put that as an additional fact that this cohomology ring has a complementary basis by the Schubert polynomials indexed by permutations that are actually inside Sn. Schubert polynomial, put a Z in front. And then the theorem that this is showing is that these bases are dual, not in a Poincare duality setting, but in terms of the natural pairing between homology and cohomology. So this is called Kronecker duality. Now, the usual Poincare duality is actually a coincidence. That one, of all these coincidences, Poincare duality is the biggest coincidence. The spurious fact about the flag variety is that the flag variety is smooth, and so I can use Poincare duality to relate cohomology classes to homology classes in a different way. So that is coincidence that FLN has Poincare duality. So there's a dual homology basis. So there is a dual homology basis X lower W, which turns out to be B minus WB. So these are the lower triangular matrices. So there's this homology basis that's dual to the cohomology basis under the intersection pairing in homology. So under this coincidence, we actually get that these XWs have class equal. So the fundamental classes of these XWs, so this is the fundamental class of X lower W in homology is equal to the class of is equal to this Schubert polynomial. Okay, that last one was it really could have been that these dual things didn't exist. I mean, okay, it was smooth. The flag variety was smooth, so they did exist. But like up to this point, B minus never showed up. B minus was not relevant. The duality is some consequence of smoothness. The fact that this is also a nice thing, kind of random. And this gives a geometric meaning to the Schubert polynomials, not just as being Kronecker dual to certain classes, but also Poincare dual to certain classes. So I think you would say that this X lower W is Poincare dual too. So this would, I guess this is saying these are Poincare dual. Right. This is a very confusing thing that I'm trying to express here. So if anyone has questions, you can complain to me now.
How do you attack the fundamental class of FLN to sort of keep cohomology and homology?
Yeah, that's rather than use duality in that. The last thing you're doing.
Yeah. All right.
That's my bills.
There exists a coincidence such that this happened. Just wait till you see what happens on my variety.
So because some of us like this coincidence, right? More neutrally,
Whoa.
saying that this will not play a fundamental role in the story that follows. Is that a way of anticipating what's happening?
It not only doesn't play a fundamental role, it almost can't play a role in what we're going to say.
Sounds good.
So this coincidence is also responsible for actually a really nice geometric interpretation of multiplying Schubert cycles. So here, if I multiply two Schubert polynomials, I get a non-negative sum of Schubert polynomials. The fact that those structure coefficients have geometric meaning is intimately tied to this coincidence. And for the family of polynomials that me and Vasu are going, that I'm going to be describing, that Vasu introduced, I guess indirectly last time, they also satisfy this non-negative expansion, but that doesn't have a geometric meaning in terms of it must have been non-negative because there was some fundamental geometry that was controlling it. It actually seems like there's a genuine geometric mystery to what positivity means when you don't have this kind of duality present. Okay, but any other questions about Schubert things? Cool. Okay. Let's just erase this. Okay. So the quasi-symmetric divided differences give a representation of the Thompson one. So I'm going to recall what these operations are. So here we're going to recall Ri is this Bergeron-Sottile map that actually genuinely reduces variables on application and has the property that Ri of f is f of x1 through xi minus 1, 0, xi through xn minus 1. And we're going to define a new divided difference operation called Ti, which is going to be equivalently defined by saying it's Ri plus 1 minus Ri over xi. Or you could take it to be Ri del I, or you could take it to be Ri plus 1 del I. Okay. So these operations satisfy the relations of the positive Thompson monoid. What this means is that what this means is that Ti Tj is equal to Tj Ti plus 1 for all I bigger than j. And this almost has nothing to do with the definition of Ti beyond this variable shifting property of these Ri maps. So it turns out if I draw the T's, so let's see what the relation T2, T1 equals T1, T3 is saying. If I want to diagrammatically represent T1, I can think of it as a map that touches two of the variables. So input is down here, output is up here. It touches these two variables and squishes them into one variable and implicitly reindexes all future variables. By reindexing all future variables, now T2 at this level is now over here. This is T2. And this is the same thing you would get if I had applied the later operation, T3, because now, although T3 is reindexing all the future variables to be smaller than what they once were, so 1, 2, you can think of this as initially as 1, 2, 3, 4, 5, 6, 7, 8, then it becomes 1, 2, 3, 4, 5, 6, 7. You can see T2 is acting on these variables. Here, if I start with the variables 1, 2, 3, 4, 5, 7, 8, 9, 10, T3 is acting on the variables 3 and 4, and then T1 at this level is now over here. So this is very, very, very basic reason that these T's are commuting in this weird way is exactly the same reason that these del operations commute. The del operations are acting on variables that are too far apart. These operations are also acting on variables that are too far apart to interact. It's just that to actually express that fact combined with the reindexing, you have to introduce this variable shift. And then this is called the positive Thompson monoid because if I take the group generated by Gj, Gi, Gj inverse is equal to Gi plus 1 for all I greater than j. This is Thompson group's F. Thompson group. So very similar to how the braid relations, if you ignore the one that says if I square it, it gives 0. That's a monoid whose group completion is the braid monoid. When you do this, you get the Thompson group. So it turns out when people express elements of the Thompson group in terms of binary trees, they're literally expressing it as like a binary tree times the inverse of the formal inverse of another binary tree that were built using this kind of building process. This is a very geometric reason why this would show up in a group indexed by pairs of binary trees. And they encode like the dyadic, some crazy dyadic piecewise linear maps between unit intervals, and the two binary trees encode the way that the input and the output are split into these dyadic intervals. But that doesn't matter. It's just a funny algebra. And another funny thing about this algebra is separately, I don't think anyone's ever written down a polynomial representation of this algebra. But if they have, if anyone out there on YouTube knows, please contact me at hunter.spink@utoronto.ca. That would be really, really great. But okay, that's my plea.
Hunter?
Yes.
So I mean, I think you're claiming this is somehow like a canonical story, but in one sense, even just for symmetric functions, are the operators del I? Like, can we say they're canonical in some way?
Oh, yeah. So, okay, I was going to admit that, but since a nice question was asked, let me tell you that del I are canonically associated to the inclusion of sim into all polynomials, okay? And how they're nice is by the following theorem. The endomorphisms of polynomials which commute with multiplication by symmetric polynomials is generated by as a Pol n module. So an obvious subring of this is multiply by a polynomial that obviously commutes with multiply by a symmetric polynomial. But okay, it's also generated as a Pol n module by the del I operations. So this, if I want to write down a map that takes polynomials to polynomials so that any symmetric polynomial can pass through it, it turns out that this actually decomposes into the direct sum of Pol n del W, where W over some set of W, W and SN. What this means is that any such operation on polynomials that can be used with symmetrics, you can canonically decompose it into apply some del sequence multiplied by a polynomial plus apply another del sequence multiplied by some polynomial plus dot 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 dot. So they really are canonically associated to symmetric function beyond just having the nice property that they produce symmetric polynomials when you apply them, and they kill symmetric polynomials when you apply them. So besides those two funny facts, there's an actual fact that they satisfy. And there's an analog of this for QSym and TI. So there's an analog for QSym and TI. So maybe I should tell you that just to say why these TIs are somewhat nice. The only difference is that now, unfortunately, the TIs deplete variables. So we have to describe a more general thing than commuting with symmetric polynomials. And it turns out that what the property is that so if I have F is quasi-symmetric, this is equal to R1 of F Ti of G. So like when I try and move this F outside of this Ti, I still need to have the number of variables go down. So you have to apply this map that sets the first variable to 0. And in some appropriate sense, all maps that take polynomials in n variables to polynomials in n minus k variables that have the property that a quasi-symmetric polynomial, when you pull it out, ends up turning into the quasi-symmetric polynomial where I've set a bunch of the variables to 0. The TIs generate in the same way. So if I just replace all del's with t's and del w's with tf's, it's the same statement. So they are canonically associated to quasi-symmetrics, modulo the fact that we have to accommodate the variable depletion in the statement of the commutation. So this, instead of end sim n pol n, it'd be like hom pol n to pol n minus k that has some special interaction with quasi-symmetrics. But you know, I think that's fairly convincing. Yes?
Should we think about these RIs as some analog of the Weyl group action in this context?
That's a good question. I would say yes. In fact, I will talk about how they're analogous. So the thing that's analogous to the Weyl group action is going to not be the application of symmetry, but it's going to be the statement of symmetry. So Ri equals Ri plus 1 should be thought of as the quasi-symmetric analog of doing nothing is the same as applying the ith transposition. But neither Ri nor Ri plus 1 is like special in any way. Like this statement can't be rewritten as saying the identity is equal to something. It's saying two transformations of something are equal, rather than the nothing transformation is equal to the flip transformation. Okay, you have to be a little bit careful, but yes, it should be thought of as yes. And I will talk about that in a little bit actually. So I'll put a pin in that. Pin. Okay. Great. So these things satisfy these relations. Now, how do we build geometric objects that are joint to these T operations? So if I want to carry out this first principles approach to Schubert calculus, but in the quasi-symmetric setting, I want to take these T's and I want to find a way to model the application of T in some adjoint way. So in order to do this, because of the variable depletion, rather than finding an endomorph, finding something that takes things in the flag variety and spits out other things in the flag variety, we're going to have to change the number of variables of the flag variety. So here's the key operation. Well, I'll call psi I minus. It's going to take n-1 flags and turn them into n flags, okay? So I'm going to describe an inclusion of the n-1 flag variety into the n flag variety, and I will do it by example. And anyone can complain if they don't understand the example, but I will make fun of you if you don't understand it. So A, B, C, D, E, F, G, H, I is equal to A, 0, B, C, D, 0, 1, 0, 0, 0, 0, D, G, E, F, H, I. Okay, so that map, you can write it out, I don't know, it like at the level of flags, it like does something. But yeah, this takes matrices to matrices and commutes with the right actions of the respective Borels. If I did psi 3 minus, the 1 would have been in the 3rd position on the diagonal. Psi 4 minus, it would be on the 4th position on the diagonal. Great. So what's nice about psi I minus? Psi I minus at the level of cohomology. So the pullback map on cohomology from the flag variety to the smaller flag variety, right, is given by Ri. Okay. So this thing where you set the ith variable to 0 and you reindex is exactly this map Ri, and that's exactly what this map does to cohomology. In the dumbest way of saying this, all the data that you get when you pull back matrices under this map lie in the 1st column, the 3rd column, the 4th column. Somehow the 2nd column doesn't have any information, so that information gets destroyed, and then everything gets reindexed, so the 3rd column's now the 2nd column, the 4th column's now the 3rd column. That's basically what the proof is, that this is the pullback map when you actually do algebraic geometry. But
This is why you call them Bergeron-Sotillier operators, right? This is what they were doing.
yes, so we're going to call them Bergeron-Sotillier operations. Bergeron-Sotillier, and it's 90, 91. 91? 98, okay. 8. Yeah, so Bergeron-Sotillier looked at more general maps where a 1 goes somewhere in here that's not on the diagonal. We'll actually need to use one of those maps where a 1 doesn't appear directly on the diagonal, but they study more general things where matrices are included by putting 1s in a bunch of random positions and then studying how Schubert cycles behaved under pullback under that map. So this is a very special case of that, so they get the glory. Yes?
So I have the question with the canonicalness. So here in the BGG story, you define the flag variety and define operations pi I. Could you have started with the pi i's and the relations you wanted to satisfy and build the flag variety in a canonical way?
Yes, but then the one thing the flag variety is nicely giving you is it's giving you an ambient space on which there are already cohomology classes x1 through xn that I can like restrict to every step of this process. You could have built the xw's without reference to the flag variety, but then what you would have gotten you would have probably a very similar construction to this would have produced, there would have been more choices. You could have accidentally produced the Bott-Samuelson resolution, for example. And then the cohomology, there's no like ambient like space that could have an affine paving unless you decide how these things fit together. So somehow this like, there's just a convenient ambient setting that I can do all of these geometric constructions with these polynomials that naturally make sense in every single object simultaneously without having to, you know, reinterpret them and glue. So the answer is you can, but you know, this is a little nicer to stay in the flag variety.
So what you're doing canonical in the sense there's a precise statement is canonical, or just because it's so nice that it's convincing?
Well, I made Schubert cycles by, well, I had to, so in the BGG story, pi I lower star pi upper star. I mean, there are other maps other than pi lower star pi upper star that act like del I. You could do pi lower star pi upper star and then move your variety around randomly. But yeah, okay, so there's somewhere, there's some place where you've like decided to not make your life terrible.
Okay.
And I think one is really convincing that like, even though there could be other operations that do this, the fact that they're acting at the level of cycles rather than homology classes kind of geometrically realizes the del I's and yeah, does something nice. Yes.
Just to follow up on this, because it's like a good point, but like if you go beyond the nil-Hecke relations, you can do this for K theory, but there's a theorem of some of your colleagues which says you can't do this for other cohomology theories. You'll get Bott-Samuelson varieties and you can't like canonically go from Bott-Samuelsons to the
Oh, I didn't know that.
Ressler and Evans and like 90s.
I like that. Okay, well, it does work for these T operations. So it turns out there are other families of operations.
Right,
You can
but if you
do something.
talk about cohomology theories,
Yeah, there's like some, I mean, okay, the more complicated your operations, the more like, for example, the Hecke action, the like Hecke operators, they can act, we need to work in the cotangent space of the flag variety. You need to pick the appropriate ambient thing in which you can geometrically encode your operations. I'm saying that the flag variety naturally geometrically encoded these operations. And for the purposes of the construction I'm about to produce of the quasi-symmetric flag variety, it'll just serve as an ambient space in which I don't have to keep track of the combinatorics of how this thing I'm building up is being created. The thing I'm going to build is independent of the flag variety. It's just super, super nice that there's this object called the flag variety that all these things lie in. There's no actual logical relationship in what I'm about to do.
But the variety you're going to construct, I think Vasu said yesterday, is not smooth. Is that correct?
It is funny.
Do it.
Okay, I'll do it. Okay. You got me. I'll do it. I'm just hyping it up now because I forgot how this construction goes. No. Great. So we defined this psi minus map. And in fact, once I've defined this psi I minus map and told you that fact in about how it interacts homologically, there's really only one thing you can do to construct the quasi-symmetric flag variety. So consider the following operation, which I'll call Ti. So this is going to take subvarieties of the n-1 flag variety, going to spit out subvarieties of the flag variety. And how it's going to work, I'm calling it Pi for what will turn out to be a good reason. How it works is you do Pix is, first I do psi I minus, and then I do pi I, then I do pi I inverse. Okay. So at the level of cycles, this turns out to equal always psi I, pi I upper star, pi I lower star, psi I minus lower star. But this is actually more nicely behaved than pi I lower star, pi upper star. Somehow restricting, pushing and pulling to the image of this map turns out to destroy all the complexities of Schubert varieties. So here's a fact, for example, of Pi. So Pi X is naturally a P1 bundle. P1 bundle over the image pi I psi I minus X, which turns out to always be isomorphic to X. So actually you just get a direct P1 bundle over the variety you started with. So in Schubert varieties, most of the complexities of Schubert varieties come from the fact that pi I push forward, pi I pull back almost creates a P1 bundle. It generically creates a P1 bundle. But some of the fibers are positive dimensional, and what ends up happening is that you have to resolve it with what's called the Bott-Samuelson resolution to get a genuine P1 bundle. Here, by what turns out to be a coincidence, this construction actually produces P1 bundles naturally through its application. There's no need to resolve anything. And in particular, applying this will take smooth things to smooth things. I'm never going to end up with something that's not smooth. So to answer your question, some of the things I'm going to make are smooth. Okay, so what's nice about this map? Let's see what happens when I apply it to a variety, which lies inside FLN minus 1. And I pair it with a cohomology class. What do I get? Well, we know the adjoint, so let's write this out. So we know the adjoint of pi I upper star, pi I lower star. And so we also have psi I minus lower star x f. Okay, the adjoint of this upper star, lower star is this del. So I can move this over and get a del popping out. And then this very general statement that push forward is adjoint to push forward in homology is adjoint to pull back in cohomology. This is called the push-pull formula. It says I can move this push forward in homology over to the other side and turn it into pull back in cohomology. So the result of this is I can just move the two geometric operations to the other side and I get x comma ri del I f. And hey, look, that's that TI map that we were talking about. So TI is applied to f as a result of applying this geometric building operation. So what is the quasisymmetric flag variety? The quasisymmetric flag variety is going to have a bunch of cells that are obtained by applying these PIs in all possible ways, starting with a point. So I start with a point, which is equal to FL, I don't want to mess this up, 1 or 0, 1 or 0, 0. FL1 is a point. Yes, start with 1. Okay, so I start with 1. Now, what we're going to do is we're going to apply PI in all possible ways. That's how we made the Schubert cells. You wanted these operations these varieties that worked with any sequence of dels. You apply different sequences of dels, you get different Schuberts. Here, you apply these building PIs in all possible ways, and you get a bunch of cells. And it turns out that just like with the pi upper star, pi lower star, these operations PI geometrically realize the Thompson monoid on the nose. Thompson monoid on the nose. So they satisfy the adjoint of the commutation relations that the TIs satisfy on the nose. So we aren't going to be creating a bunch of spurious varieties. So it's not like, oh, I'm building every possible Bott-Samuelson variety and I have like n factorial varieties. No, no, no. I'm going to have one variety for every single tree that I have in my picture. So I'm going to have, so if F is expressed in the Thompson monoid, so if F corresponds to Ti1, Ti2, Tik, so if this is the operation, this is the trimming sequence of I1 through Ik, is that trimming sequence that Vasu was talking about that give you a way of depleting a forest down through contraction of these lower wedges, we're going to create the variety x of f, which is going to be these operations in reverse order, pik minus 1, pi1 point. It turns out it doesn't depend on the point. I mean, it doesn't depend on the sequence. Okay, now, okay, so I will talk longer. I was told this is
We have time.
a what?
We have time.
Okay. Okay, yes, I know, but if anyone wants to leave, I will not be offended. I'm gonna tell you a very interesting equivariant story. It's gonna be beautiful.
Sorry, when you said it doesn't depend on the sequence, you mean it only depends on the tree?
Yeah, it only depends on the tree. So I'm saying x of f rather than x of this sequence. So somehow the fact that a Schubert variety has many Bott-Samuelson resolutions that all kind of resolve it, that doesn't really matter too much because it's already independent of the choice of sequence. You get this lovely variety that's already an iterated P1. Iterated P1. Which is also called a Bott manifold. So this is an incredibly nice phoric variety associated to a polytope, which looks like a messed up cube called a combinatorial cube. Okay, so what's nice about these x of f's, of course, is that, let me just record this for posterity so we know what we're seeing. And then I'll say theorem that is going to be proved actually by moving into the equivariant world in a very interesting way. So theorem, the first one is actually, I've already proved it for you. I've already proved the first part of this theorem, but it's still a nice theorem. Pairing x of f with some polynomial, f is an f a polynomial, poly, is equal to f0 t f of f, which is the coefficient of the forest polynomial that was never defined combinatorially, but who cares? The forest polynomial, x1 through xn, in the decomposition of f, in the forest decomposition of. So just like pairing with the Schubert cycle tells you the coefficient of a Schubert polynomial in a cohomology class, pairing with this thing tells you the coefficient of a forest polynomial in this class. And the proof is, well, I won't even repeat it, it's exactly the same as what happened in the Schubert case. The no changes, except now the operations are t's instead of del's, but nothing changed, okay? The fact forest polynomials exist, combinatorial thing, you have to do something. But, you know, this operation, all that, that was just formal from the geometry. The second thing, which I think is more interesting, the union forest supported on n of these x of f's, which I'll call the quasisymmetric flag variety. So that's the quasisymmetric flag variety. Has an affine paving by the open x of f's, okay? And the cohomology ring UFLN is equal to the quasisymmetric coinvariants x1 through xn mod q sem. So instead of quotienting by symmetric polynomials with zero constant term, I now quotient by quasi-symmetric polynomials with zero constant term. And this also has a basis of forest polynomials. So the basis f supported on n of z forest polynomial f, exactly the same as with Schubert's. And there's a homology basis because of this affine paving. The homology basis of QFLN is the direct sum of Z x of f, where f is this forest. So it's a very find and replace kind of theorem from the classical one. Yes.
When you say forest supported on N, do the trees have to cover every vertex or just be contained there?
Right, so that's a good question. So okay, so let me tell you what just happened. This construction, as I literally said it, produces the top dimensional cells in the quasi-symmetric flag variety. Because when you do these operations starting with a point, you end up building a tree that completely covers everything. So it's a tree of maximal size. To get the other trees that appear in here, you basically just start at an intermediate flag variety, point in an intermediate flag variety, and apply these building operations, and you get all the other cells coming in that way.
And now I care.
It's always the identity. It turns out it's always the identity. It's just the identity. So I'll say identity in some FL n minus k. Right. And that was a little bit weird because some of these cells are actually contained in the other cells. Or maybe that's not weird because that's what happens with Schubert cells. So okay, so here's what's happening. All these things are smooth. All these things are smooth. The way you should think about this, so there's something fundamentally weird about it. It's reducible. These top dimensional cells all have the same dimension. So unlike the flag variety has one big top dimensional cell. That top dimensional cell is called the flag variety. Everything is contained in the flag variety. Whoop-de-doo. Here, we have many top dimensional cells.
Sorry, Hunter, isn't the dimension k?
Well, if I start with id in FL0, then I'll get something of dimension, FL1, I'll get something of dimension n minus 1. So depending on which, so to get the maximal dimension ones, you start with the point in a really small flag variety, and then you build it P1 bundle a lot of times. If you want really small cells, you start with the identity in some very large flag variety, and then you only have to do this P1 building a few times. So you get different sizes of cells depending on where you start with the identity and then apply this operation sequentially.
Okay.
Yeah. Right. In the case of Schubert calculus, you started with a point actually in the full flag variety and then applied operations a bunch of times. Yes.
Wouldn't it be clear to say that like this XF you described is not a cell? Right? It has a cell decomposition.
Oh, top dimensional cell
That's a cell
closures.
closure, and
Yeah.
and so there's many cells inside that are smaller dimension.
Yes, but okay, just like with Schubert varieties, there's like a God-given open, like even though it's like a complicated CW complex, you choose a specific affine in it to be its favorite affine.
Right.
Okay, so when I say that there's an affine paving, I mean there's a very specific affine chart inside this, inside these cell closures that has the property that you build it up out of these affine charts. And those affine charts turn out to actually be dual to the K-theory version of these things as well. So they are the absolute correct analog of the open cells in.
But in the K-theory setting, how do you, I mean, these things aren't smooth, so you don't really have a product on the K-theory or anything like that. So I'm not sure how you could.
Well, we have to be a little bit careful. So one thing that I'll point out is every individual thing is smooth. We just fit them together in some weird way. Now, this is actually not that bad. If I think about Schubert calculus, here's the thing you could do, thought experiment. I start building Schubert varieties. So I start, pi lower star, pi upper. So I do it in a bunch of ways. And then as soon as I hit the number 12, I go, I don't want to build any more Schubert varieties. Stop, pull the switch. I don't want to build any more of the flag variety. What you'll end up with is a complex of varieties whose cohomology ring and K ring are actually very nice. They're just going to be the cohomology and K rings. It's going to be like operational K theory. It's not going to be. I know there's like a bunch of K theories. There exists one K theory for which this is reasonable and works.
So it's going to be the linear dual of the K homology.
Thank you.
Is that what you're Sorry, because you want all these dualities.
Yes, I want the one you said.
So this canonical affine paving, I'm a little bit confused. What is there one?
There is an affine paving. So let me draw a picture. Let me draw a picture.
I agree there is an affine paving, but which one?
Whoa. It's not obvious there's an affine paving. So okay, let me
Yeah.
draw something that doesn't have an affine paving and something that does have an affine paving. Okay, so this is what I would call a reasonable misconception. I have a bunch of things which are nice projective space, bundles of projective space. Every part is nice. They're put together in some way. Obviously, there's an affine paving. So for example, if I have two P1s like this, there would be an affine paving. The affine paving, so if this is a P1, this is a P1. I'm going to be very specific. In affine paving, I want to build this thing up one affine space at a time. So this happens to have an affine paving because I can take this affine space, A1, and then what I'm left with is the remaining P1. So then I can take this part of this P1. So this is piece 1, piece 2 is A1, and then piece 3 is this A0. And you get the disjoint union of those three things is equal to the union of these two P1s. So that seems reasonable. I have two nice things put together in a weird way, and there was an affine paving. Here's an example where there isn't an affine paving. No affine paving. One way to see it doesn't have an affine paving is if it has an affine paving, by a spectral sequence argument, you can show that there's no odd dimensional homology. But this has odd dimensional homology if I glue P1s together in this way, because I can go around a circle. I can literally do the circle class. This is like the circle, a circle embedded inside this going through these 3 points. That is a genuine, non-trivial homology class of dimension 1. But if there was an affine paving, it couldn't work. So what the reason that there isn't an affine paving is if you start trying to build this up out of affine pieces, like literally A1s, you're going to run into trouble. You'll need to use GMs or like affine lines with more punctures. I mean, the affine paving is specific to affine spaces.
That is the disjoint union of three A1s.
Yeah.
But it is.
The gluing relation
Yeah,
matters.
gluing is, so paving, you want something like stratification, you
Yes.
want.
Yeah, so it has to be stratified in this way where the union of the previous cells is. So that's.
No, my question was much simpler. Was the affine paving of single XF? Which
Okay.
one?
Just remove the smaller XFs?
Wait. So each individual XF. Okay, so individual Schubert cells, do they have affine pavings? I don't think
They are affine.
No, sorry, individual Schubert cell closures.
Yes.
Schubert varieties?
Yes.
Okay, great, okay. These X of Fs also separately have their own affine pavings. That affine paving is unrelated to the paving of the flag variety that you create using the BWBs. The affine paving of the individual cell closures is a nice feature the cell closures have, but is not related to this affine paving that I'm talking about here. So there's always an affine paving. So being an iterated P1 bundle gives you this affine paving because if I have a bundle of P1s, I can split that into basically a bundle of A1s and then a bundle of like a point corresponding to some section. And then that will allow you to recursively create, that'll allow you to recursively construct an affine paving.
Wait, but what?
Of the cell
XF or
closures.
the union?
Both X of F and the union have affine pavings. For the purpose of this theorem in connection to Schubert calculus, the relevance is that the affine paving of the whole thing. So let me maybe draw a picture of what happens in 2 dimensions. Would that help?
These are Bot-Samuelson varieties, right? Like they're special, very special Bot-Samuelson varieties.
They're Bott manifolds. They're not like isomorphic to Bott-Samuelson varieties, but okay.
No?
No, because of these R maps or.
Okay.
Well, one thing is that the degree map on a Bott-Samuelson variety is encoding the constant term of applying a bunch of divided differences, whereas the degree map on our thing is the constant term of these t's, which have these r's interleaved in them. So it might be abstractly isomorphic randomly to some Bott-Samuelson variety, but it's not going to be canonical. Like if it happens, it's a coincidence.
Bott manifold, you mean iterated P1 bundle where every P1 bundle has a section?
Yes, that's what I mean. Yes,
So the pi I are G equivalent, right?
yes.
And how about psi I?
Psi I is torus-equivariant for a very specific action. You have to choose compatible actions of the toruses on FLN -1 and FLN, but it's torus and is actually invariant under GLN -1 if you imbue GLN with this crazy action of GLN -1 by acting in this weird way that doesn't touch the I throwing concept. But
So you're applying paving is equivariant, alternative equivariant.
yeah. So these are all toric varieties. Okay, so I want to draw an example of. Sorry, a few more questions. Sure, why not? You?
So the indexing, cohomology indexing set are these like smaller trees for that time paving?
It's unions of trees that are plonked on the numbers 1 through n. So there can be multiple trees. And then if there are multiple trees, it corresponds, then it's isomorphic to a product of the individual things that you would get by considering one tree at a time. So it actually splits up according to how the forest is split up into the trees.
Are there maps to flag varieties, like from F?
Yes. Yes. There are maps. From what?
From the XFs to the flag variety.
So X of F is naturally embedded in FLN. If it corresponds to a disconnected forest, then there is a natural way in which it comes from a product of smaller flag varieties. There's some diagram that commutes that says the ones that are disconnected actually come from a from a product of flag varieties.
You said something new just before the question. You said this is a toric variety.
Sorry, X of F is a toric variety.
XF is a toric variety. Oh, so that's a proof that it cannot be a Bott-Samuelson.
Bott-Samuelson varieties are toric varieties. That's
Some are.
Some are.
Only some of them are. So.
I mean, with respect to what torus, you can always give a Bott-Samuelson variety a big torus action.
Splitting and that influence.
Oh, so Bott-Samuelson, you
I don't-
find the torus?
I don't know that that's true. I think that they're diffeomorphic to toric varieties, but I don't know that they have the algebraic.
No, because you literally just imbue the fiber. So
Some of them are toric varieties. This is a fact.
If you do what you're trying to do,
Right,
some are.
So these are fairly special things, and it could be that they overlap with Bott-Samuelson variants.
What you're doing
Yeah.
works on a patch, but you can't extend the character to the other patch in a way that makes it still be a character on a torus 1 dimension bigger.
Sure. Yes.
So if I still may, so every single XF is an iterated P1 bundle,
Yes.
right? Now we take their unions.
Yeah.
Does this union intersect also along XFs just for
Well,
other?
why don't I draw a picture of the two-dimensional case? Any other questions before I draw this stupid?
Myself is-
Okay, so being the iterated P1 bundle that it is, under some assumptions, but I'm pretty sure there are no assumptions. I can prove that they're all toric varieties, but whatever. It doesn't matter. We're working I think because we're working in the holomorphic setting, there's no like issue of choosing, like we're not choosing crazy line bundles and to take projectivizations of.
The torus of FLN acts on yours.
Okay, anyway, it doesn't matter. So, okay, here's what this is. Okay, so if I have a so if I have an iterated P1 bundle, iterated P1 bundle, and let's say under nice hypotheses, then this is a Bott manifold means it's a toric variety whose moment polytope is a combinatorial cube. Okay. So what is a combinatorial cube? It means that the face lattice of the polytope is the same as the face lattice of a cube. And because of some theorem, this means that it can be iteratively built out of smaller combinatorial cubes by the same process that you build a Hirzebruch surface. So if I have a P1 whose moment polytope is an interval, and I have another P1 whose moment polytope is an interval, it doesn't matter what their lengths are, both of these would represent P1. If I draw the linear interpolation between those two realizations of the P1, then this gives me the moment polytope of a new toric variety that is built out of, so this is a P1 bundle over P1. And here are these two smaller P1s, the realization of these polytopes correspond to the two line bundles L1 and L2. So that's the projectivization of L1 plus L2. This goes back to like, okay. So when I was saying Bott manifold, when I was saying Bott Samuelson, this is what I mean. I mean a construction where you're projectivizing not even a random rank 2 vector bundle, but actually a direct sum of two line bundles. And when you do this, this will always have a section because I can twist by the inverse of this line bundle. This is really the projectivization of a trivial bundle plus another line bundle. So you can always take a section and then it's
two disjoint sections. So
that's two disjoint sections,
Bott
even better.
Samuelsons always have sections, but they don't have two disjoint ones. So the torus action extending is the two disjoint sections.
I see. Okay, these have two disjoint sections. Thank you, Dave. That's a good point. Okay, so they're very special. The nice hypothesis is this. You always get it by taking a projectivization of a split rank 2 vector bundle over the previous thing. Then you will always get a combinatorial cube as the moment polytope.
That's what you mean by XF is a toric variety.
These are toric. They are toric varieties, but they're toric varieties whose moment polytope is even nicer than a random toric variety. It's a cube.
I'm really sorry, but I thought it's a P1 bundle over a flag variety.
No, these things are, you start with something small, like a point, P1 bundle over. Well, it was over FL1, so it's kind of.
Not all.
But you start with a point inside, you start with the identity point inside some flag variety. And then you go P1 bundle, P1 bundle, P1 bundle, P1 bundle.
Okay, thanks.
And the way it sits in the learning. Cool. We have this iterated P1 bundle. Let me show you how it glues together. So, okay, so I'm going to draw how these P1 bundles glue together by drawing their polytopes and showing how the polytopes are stuck together. And then you have to imagine the moment map for yourself, because I can't draw two complex dimensional things. I can only draw two real dimensional things.
Can you tell us what either the trimming sequences or forests are labeling bases along the way? Because I think that would.
I'm just going to draw, yes. Well, I have to, it's really small. It's going to be fine. Okay. Okay, so here is, okay, so when I'm going to write down permutations that are indexing these things. What I mean is, this really means the image under the moment map, the permutation matrix associated to 1, 2, 3. So I don't want to write mu of permutation matrix associated to whatever in this. Okay. So this is what it looks like. The top dimensional things fit together like this. So here's 1, 2, 3. Here's 3, 1, 2, 3, 2, 1, 2, 1, 3, 1, 3, 2. So the two top dimensional things already fit together in a pretty bad way. I mean, not a bad way necessarily, but it's like a weird way. You know, it's not like they're glued along a P1. These are two Hirzebruch surfaces glued along P1 and another P1 that are embedded inside this Hirzebruch surface. One is horizontal to the base, one is like a fiber, and then they're intersecting at this point, and then, you know, it's glued together like this. Okay, so this is what the top dimensional things look like. What are the lower dimensional things? So the lower dimensional x of f's are actually, so I'll draw them in colors. So the top ones are, actually, I'll draw the open cell. So here's the open cell associated to this top dimensional force. So this corresponds to this tree on 1, 2, 3. This top dimensional cell corresponds to this tree on 1, 2, 3. There are two biggest possible trees I can draw on 3 elements, and I've drawn them. The half open cell, that's the that corresponds to the affine chart, is I don't include this face, I don't include this face, I don't include this point. Okay, and now this is associated to that piece. Again, it's kind of funny how they're fitting together and being paved, but this is the correct way to pave it. Okay, and then I have 2, 1, 3. So this is going to be this circle. So this corresponds to this tree over here. Then I have this over here, and this corresponds to this tree over here. And then the last one is just the identity inside the flag variety. So in the most extreme case, I didn't apply any P1 building operations. I just started with the identity. So then we have one last one in a color that doesn't even exist because any more hydromal color is white. This single point corresponds to this.
So why don't you have the tree joining the first and third vertex?
The same reason why, when you consider the paving of the complete flag variety, you don't, it has nothing to do with the pavings of the individual Schubert cells, the cycles, beyond the fact that the largest piece happens to be in common.
Wait,
Like-
so you're saying that tree exists, but it's not. That's not like.
Wait. That's not true. The paving of the complete flag variety
Yes.
Is,
restricts to the paving of the shoe itself.
Each connected.
okay, that's a good point. Everyone's saying good points, just everyone calm down. Calm down. All right, I didn't want to go into this detail. Okay, so basically, all of the other, okay, fine, I'll tell you this. Like, you want to know,
We want to.
you want to know what all these other pieces correspond to? These are the important ones. The other piece, fine. The other piece is what they correspond to is the following thing. Okay, so when I told you there was a psi I minus map, what I might have failed to tell you is that there's a psi I plus map. Psi I plus of x is psi I minus x, and then the operation of swap columns I and I plus 1. So the net effect of this is insert 1 into location I plus 1. So you put it 1 over 1 to the right, I mean into the so on the diagonal it'd be like here. So it'd be there's a 1 just off the diagonal. So this is I, this is I plus 1, and then there'd be zeros here. These zeros here. Okay, so this is just a related map you can do that inserts a 1 into the location I plus 1. And then all of these pieces, so all pieces are indexed by composites, distinct composites of psi I minus, psi I plus, and pi in all possible orders. So it turns out that there's some horrible monoid that controls when different composites of the maps psi I minus, psi I plus, and pi, when they are equal to each other, they're local relations, but there's like 13 of them. And if you equivalence classes in that monoid under those 13 relations that they necessarily satisfy for obvious reasons, of course, are in bijection with this square, this square, this line, this line, this line, this line, this line, this line, this point, this point, this point, this point, this point. So you get the points by only doing the psi I minus and the psi I pluses. So this is what the special permutations are those things that you can get by only applying these inclusion maps that are take permutation matrices to permutation matrices. This insert of one thing will preserve being a permutation matrix. So when I apply it in sequence, I start with the identity permutation somewhere, and I do these psi's, and it includes, it does this. Okay, and then when you do this, so distinct composites of this, starting with FL, starting with FL1, which is just a point. Okay.
So the psi i's preserve fixed points, that's what you're saying.
Yeah, so they preserve fixed points, and the p's kind of interpolate between fixed points.
You can do equivalent localization, that's.
But
Yeah.
the P's tell you which forest you're in, because each of these cells is the closure of one of these is some smaller PF, I guess, from what you said.
Okay, so now how it works is in order to,
XF, I mean.
okay, so now there's two things. So one is, so the distinct composites give you these distinct cells. Some of these cells turn out to be isomorphic varieties to each other. They turn out to be isomorphic in a very specific way that if I translate them back to the origin using the bottom element as the inverse translation to act on the left, then some of these cells will collapse onto each other. And basically there are some nested forests that index the distinct composites non-equivariantly. These composites index the just different combinatorial forest data indexes all the possible questions you could have. Questions like, what are all of the cells touching the origin? What are all of the, what are all the distinct cells? So all of these things, there's a combinatorial object that encodes it, and it's all some variant of nested forests.
But each of the but the cell that you wrote down there that the XFs give a basis for homology, so presumably the closure of each of one of these cells is an XF. Is that right?
Well, so for example, the closure of this is not one of these XF. I drew the 5 XFs here. So this
Red thing is not XF.
yeah, so I drew orange, green, blue, red. So blue was included all the stuff in the middle. And red included all of this.
But when you said that the homology had a basis by this, you were saying it was from the affine paving. Ordinarily, the basis of one X is the closures of the cells in the affine paving.
Yeah, so I have 5 cells in this affine paving. They are red, blue, orange, green, and white.
Those are not but the closures of those are not the XFs?
The closures of those are the XFs.
Oh, okay.
And then people started asking, what about all these other edges that I didn't talk about? And then I had to introduce more combinatorial data to describe that. But that's irrelevant for the purpose of the paving of the flag, quasi-symmetric flag variety. Yes.
So 231 does not show up.
231 does not show up.
So
Great. Yes.
what are the permutations that don't show up?
That's such a good question. Wow.
So is this a subgraph of the Bruha graph? Maybe that's.
Also good question. Wow. 2 questions that actually progress the talk. I'm so happy. Oh my God, I was not. Jesus Christ. All right. Okay, so to motivate which permutations show up, let me tell you what the psi I minus and the psi I plus do at the level of functions. So non-equivariantly, without a torus action, they don't do anything except plug in 0 into the ith or the I plus first spot. Equivariantly, you have an extra set of variables. Extra set of variables T1, T2, that are encoding the characters of a torus acting on the space. Here the torus is diagonal matrices. Diagonal matrices. And these operations x I minus 1 t I x I so minus 1 they stick a ti into either the I or the I plus first position. For a general pattern map, if I'm sticking a 1 into a random place, the column is telling you where you're sticking the t in, and the row is telling you what t you're sticking in. So by choosing to do I or the one next to it, I plus 1, this corresponds to sticking a t into the ith position or the ith plus first position.
The previous ones were on spaces. These are on polynomials. So maybe you want psi I minus star or something.
Oh, yes, star. Thank you. So I'll call this Ri minus of f. I'll call this Ri plus of f. So these are just two variants of Ri. Now notice non-equivariantly, so without this extra set of t variables, if the t variables are 0, Ri plus is the same as Ri plus 1 minus. Because sticking ti into the I plus first spot and sticking ti plus 1 into the I plus first spot is exactly the same thing. So non-equivariantly, psi I plus is equal to psi star is equal to psi I plus 1 minus star. So it's not necessary to introduce all of these variants of R non-equivariantly. We just have R1 and R2 and R3. Here, there's a difference, it turns out. And this equality is what's going to be governing this notion of equivariant quasisymmetry. So, and it's going to give the equivariant divided differences. So definition, f of x1 semicolon t1 is equivariantly, I'll put it to xn, is equivariantly quasisymmetric if Ri plus f is equal to Ri minus f for I equals 1, 2, and minus 1. So now instead of 0 being allowed to move through the list, this is locally saying the I and the I plus first variable have their favorite version of 0. It's called ti. And that's the thing that's allowed to swap between them. So you get this weird thing. It was actually difficult to try and move variables through this list using this restricted symmetry. But now let's play a game. Let's play a game called, that will answer your question and your question. Let's play a game of how strong is this definition of equivariant quasisymmetry. So how we're going to play the game is as follows. I'm going to suppose that I have something that is equivariantly quasisymmetric, x1, x2, x3, t1, t2, 3. So I'm going to assume that it's equivariantly quasisymmetric. So that means that f of, I'll just not write these variables anymore because it's annoying to write them. T1AB is equal to a f of a T1B and f of a T2B is equal to f of a B T2. So let's say that I know only this about my polynomial in two variables. What does that tell me about the evaluations of the x variables at these t variables? So what I'm going to do is I'm going to start with f of t1, t2, and t3. And now someone in the audience tell me what another permutation of the t's I could stick into the x's that would be equal to this substitution. So I want to go equals and then some other substitution.
T2, T1,
T2, T1, T3. T2, T1, T3. Great. And you were allowed to do that because T1 was in the first spot. You instantiated the first rule. This first restricted symmetry is being used. Now you're not allowed to switch 2 and 3. T2 is in none of the spots that allow you to instantiate the second rule. So you're actually stuck there. Okay, let's go back to the beginning. What other permutations can I get from T1, T2, and T3?
T1, T3.
Right. T1, T3, T2. Okay, so what's another permutation I can get? 3, 1, 2. T3, T1, T2. What's another permutation I can get? 3, 2, 1. And you cannot get 2, 3, 1. You can get these five permutations are naturally embedded into the definition of equivariant quasisymmetry, but you cannot get 2, 3, 1. So, which permutations can you actually get? Because you all bullied me into answering a bunch of crazy questions, I'm going to recall what all of these permutations look like for 4 elements. Okay, let's do this. 1, 2, 3, 4. 1, 2, 4, 3. So I can swap that. Then I can swap to 1, 4, 2, 3, 4, 1, 2, 3. Then I can go 4, 2, 1, 3. Then I can go 4, 3, 4, 2, 3, 1. Then I can go 4, 3, 2, 1. And then I can go maybe up here. I can go 2, 1, 3, 4. And then I can go 2, 1, 4, 3. And then I can go 1, 3, 2, 4. And then I can go 3, 1, 2, 4. And then I can go 3, 2, 1, 4. And then I think I also could have down here done something crazy where I went down and I go 4, 1, 4, 3, 2. And then 4, 1, 3, 2. And then I think it would have also been possible to go from here to here. Okay, so these are the 14 permutations. So more data for all of you to guess what's special about these permutations. That's kind of tricky.
Are they in such a pattern?
Is everyone avoiding or something?
43.
Nope.
Oh, there's.
I think this is harder. I'll tell you what it is, because it's funny. So what it is they're the permutations obtained by the following process. Draw a non-crossing partition. Here's a non-crossing partition. I'll do it for a couple of examples. This is a non-crossing partition. A non-crossing partition is a bunch of bumps so that they don't cross, and I'm drawing the bumps in sequence. So every part of the partition I encode by going bumpy, 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 bump. And then 2 bumps are not allowed to cross, but they're allowed to nest. Okay, and then on each of these bumpy, bumpy bumps, I put the value of the number, I put the backward cycle on this part. So here 1 goes to 4, 4 goes to 3, 3 goes to 1. And now I check, 4, 2, 1, 3 is here. Oh, perfect. Okay, now let's look at this one. 1 went to 4, 4 went to 1, 2 went to 3, 3 went to 2. And there we go. These are the non-crossing permutations. These are the permutations which are non-crossing. So these are the Catalan non-crossing permutations associated to Sn minus 1, Sn minus 2, S1, which would be backwards long cycle. So there's just some crazy definition that you can look up about that called non-crossing permutations associated to a, so for every way you can multiply the distinct adjacent transpositions, there's some weird version of non-crossing, but for the product in order of the adjacent transpositions, it turned out to literally mean that they don't cross. So yay, they don't cross. Right, so these are the permutations you can get. This is not the GKM graph. So this is the analog. This, I would call this the restricted Cayley graph. Cayley graph. That's not what controls the geometry. What controls the geometry is the graph you get by connecting two of these things if they differ by any transposition. So that would be the Coxeter graph. So for example, I could switch, I would have an edge directly from here to here that encodes, that would be labeled with T3 minus T1. That's encoding the fact that 3 and 1 have swapped places with each other. So if I draw those dotted edges, it's going to look pretty bad. But if I just draw these single edges, it's kind of funny. Okay, so these would be the 14 things that would occur in the next dimension. It would be, there would be 5 top dimensional cells, 14 cells total, and they would again pave into this lovely picture. And okay, so what's nice is, okay, so there's a nice definition of equivariant quasisymmetry that and I have this cell decomposition into these cells. It turns out that the double version of all of these stories holds true. So there are these polynomials called double forest polynomials, and they are adapted to the operations EI of F, which is Ri plus F minus Ri minus F over Xi minus Ti. So the presence of I plus 1 and I in the non-equivariant story, the I plus 1 was secretly an Ri plus. And now, so when I substitute Ti into the ith position or the I plus first, we see that the difference of the two is going to be divisible by Xi minus Ti, and that's what I'm allowed to divide out by. So there's a family of polynomials adapted to these EIs called the double forest polynomials, and they form a flow-up basis with respect to the GKM graph associated to this complex. So it's literally how double Schubert polynomials, so let me say the property that double Schubert polynomials have. So double Schubert polynomials have the property that, so they're a double version of the single Schubert polynomials, and they have the nice property that if I evaluate the x variables to W prime, to y W prime of 1, comma, dot, 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 y W prime of n, then you get 0 if W prime is not greater than or equal to W. You get a very particular product of yi minus yj's, where I and j are inversions of W. If W prime equals W, and you get a positive, a Graham positive formula otherwise. Graham positive formula otherwise. Graham coming from Graham Cracker. No, from Bill Graham, who was nice enough to show up to this talk today. Thank you very much. Okay. Great. So, great. Okay. So now the theorem that we have, is that these double forest polynomials, TF, are the same for the restricted GKM graph. Restricted for GKM graph are restricted to these non-crossing partitions, permutations. So that means that if you want to interpolate a polynomial on the non-crossing permutations, you would use the double forest polynomials because they're upper triangular with respect to evaluations at the permutations. You could solve for the coefficients one by one of these double forest polynomials. Yes.
So your quasi-symmetric flag variety has an equivariant embedding right inside the flag variety. So
Yes, so it naturally lies inside the flag variety, and the inclusion of it is torus-equivariant because inclusions are invariant. Yes, it's with that embedding that we can relate it to the usual flag variety.
We did that torus, the torus of the flag variety.
Both the torus, all the toruses that we're using are the torus of diagonal matrices, and they're acting on all the objects that have been presented in this talk. Yeah, so they form this upper triangular basis, and they're dual to the cells equivariantly. So same as the double Schubert polynomials are not just dual to the Schubert cells in non-equivariant cohomology and homology, but also equivariantly. And they form a basis. I mean, it's just all these statements would be boring to write down. I just put y's everywhere. But just like any statement you can imagine about double Schubert polynomials, the same thing holds for forest, as long as you restrict to these very particular non-crossing permutations that come from these adjacent swarms. So to end this off, I want to say one nice thing.
Can I ask?
Yes.
Is there a Cauchy formula for it?
There's no Cauchy formula. And is related to the lack of dual classes. So the fact that Schubert polynomials have a double Cauchy formula is related to the fact that one of these two variables is encoding the opposite Schuberts. And there is no analog of that for double forest as far as we can tell. But okay, so here's the nice thing. So I'll tell you the final nice thing. So I want to tell you about gram positivity. So being gram positive means that you lie inside this ring. So this was studied by Professor Graham. And what it was shown is that any T invariant subvariety of the flag variety expands naturally into Schubert cycles with coefficients drawn from this ring. And then all the coefficients are non-negative, so when you specialize to all the T's to 0, you recover the usual fact that varieties expand positively into Schubert varieties. And here in the quasi-symmetric flag variety, we have positivity statements. So one thing is that PF, PG is the sum of A, H, F, G, P, H. These things are gram positive with a combinatorial proof. Gram positive. And you can also decompose Schubert polynomials, double Schubert polynomials of X T is equal to a sum of A, W, F, P, F of T. These are gram positive for, again, combinatorial reasons. So usually you would argue using geometry. We have explicit straightening rules that let us show all positivity statements combinatorially. And then this in particular specializes to a very nice thing that a double Schur polynomial expands into the sum of our double fundamental polynomials, A, W, F, where F indexes a fundamental quasi-symmetric. So these are like the natural positive basis of quasi-symmetric polynomials, analogous to how Schurs are the natural positive basis of symmetric polynomials. And you again get X, T, you again get positive expansions, which obviously strongly suggests that this is the right definition, because whatever definitions you're using, if you don't have positive expansions into other things, then what are you really doing? But all the algorithms are explicit combinatorially, but we understand so little of them we don't know what these coefficients are in the most simple possible cases. Like we don't have a Monk's rule, we don't have a Pieri rule, we don't have anything other than our algorithm terminates positively. But if you actually studied the algorithm, it would be extremely difficult to extract what the actual coefficients that arose there are. Okay, that's.
So for us to speak for a little more with more questions.
Please, I heard. Yeah.
Can you say a little bit about how the HHMP decomposition of the pentaedron appears in this story?
Yes. So it turns out that these things that are created through this process are exactly. Okay, so these are the Richardson varieties that appear in the HHMP story. There are, so C is the backward cycle, and n minus 1, 1. And W is an Sn with the property that W of n equals n. So there are n minus 1 factorial of these Richardson varieties whose moment polytopes make a cubical decomposition of the bromidahedron into something combinatorially equivalent to a box is decomposed into smaller unit cube boxes. So there's n minus 1 factorial of these. But it turns out that if you left translate by the bottom permutation, there's an immense amount of literal collapsing that occurs. They're literally translating each other, and they all smash onto each other, and a bunch of them get identified into some things that are exactly our cells that appear in this decomposition. So we have a paper right now out, me and Vasu and Philippe, where we actually didn't realize you should do this translation, but we also did it non-equivariantly, so it didn't matter too much. And we said, wow, all these cells in the HHMP decomposition of the bromidahedral toric variety into, in this torus degeneration, all these things fit together super nicely. They all compute these evaluation at 0 of T operations applied to a polynomial. And then we were like, there's like, there's so many of these that compute exactly the same degree. And then we said, okay, you could, if you were a lunatic, translate them all to the origin, and then there's a magic collapsing that occurs. And then it wasn't until we ran into Nantel Bergeron and Lucas Gagnon that we took extremely seriously. Well, what if that was, you get a messier complex of cubes, but you get the correct equivariant picture. And it just never occurred to us to study something like this. The combinatoric showing that there's a paving is quite horrendous. This is not a simple complex of varieties to study, but it is true. Yes.
I guess the second question. So, these polytopes appear, so Carl Leon has a way of thinking about the degeneration of the pentaedron into a union of these toric Richardsons.
Mm-hmm.
Does the pentaedron variety appear anywhere in this story, or does this collapsing just completely destroy that story?
So the collapsing, okay, so one way the bromidahedron appears in that story is that obviously the individual cells that appear in Vasu's talk, he explained how each of those cells corresponded to one of these T operations. So you get this nice factorized expression T1 times T1 plus T2 dot T1 plus Tn minus 1. Here, when you collapse, you don't get an analog of this formula. So it really genuinely seems like there was an amazing combinatorial object with all of these beautiful properties and this factorization. And then separately, it's also amazing that you can disassemble this beautiful object and reassemble it into a completely different, amazing object with disjoint, interesting properties. We weren't expecting that, of course, since that's like not a very common thing to happen in math, as far as I know. Yes.
So maybe you mentioned here the connection to this expansion in the forest of the double shores, but are there other like lifts of Schur function, other quasisymmetric lifts of Schur functions of nice expansions?
So there are other things people have called. So there have been other attempts at defining quasisymmetric, equivariant quasisymmetric polynomials, and there have been attempts to extend Schur functions to quasi-symmetric ways. This has been done. The way that those extensions are connected to quasi-symmetric polynomials is fundamentally different from how these are connected to fundamental quasi-symmetric polynomials. And there is, as far as I know, there isn't, there's disjoint geometry that controls those extensions that's unrelated to this geometry. The other geometry is like Macdonald polynomials, which doesn't naturally show up in our story yet. But probably not. Yes.
So Bott-Samuelson varieties, they canonically and diffeomorphically degenerate to toric varieties. Could it be that these toric varieties are your XF?
These toric varieties are our X. Sorry, what?
Bott-Samuelson varieties canonically and diffeomorphically degenerate to toric varieties.
Okay.
Could it be that those degenerations are your XF?
So one thing is that the degree map on a Bott-Samuelson variety computes something fundamentally different from what these are computing. It might be that there's some kind of degeneration of a Bott-Samuelson variety that allows you to see this combinatorial formula geometrically.
But the degree map disagreement does not rule out this possibility, because degree map, you are looking at a specific collection of line bundles.
Yes. What do I want to say? So if you okay, so one thing is that degenerating something like a Schubert variety into smaller varieties actually doesn't correspond to a decomposition of the Schubert polynomial into smaller polynomials in general. It's in this adjoint picture, it's the fact that these cells are Schubert positive is what's being reflected by this formula. It's not, we're not taking a Schubert variety and trying to write it as a linear combination of these Schubert cells. That would not be Graham positive. You have to do it the other way. The cells are expressed with positive coefficients in terms of the Schubert cycles, and that positivity is reflected here. So I think because when you do it the other way around, we have to be very careful, because the forced polynomials can't represent anything geometric in the flag variety because they are not Schubert positive. They refine Schubert polynomials, and as Professor Graham has shown, everything geometric in the flag variety is going to be Schubert positive. So because our things refine Schubert polynomials, it's always the other way of how do you break up these things into Schubert varieties. And one difficult part of that is that these are kind of irreducible torus orbit closures already. So there isn't really a nice geometric way to break these things up any further into torus invariant things. They're already kind of as small as they possibly can.
Degeneration of Bott-Samuelson does not happen inside black variety or anything like that. It happens inside a very complicated thing.
Oh, maybe there's a way to connect these degenerations. I would be very interested, because our algorithms are very combinatorial and presumably have geometric analogs to them. But as far as we know, we just have a bunch of rules for moving R's past T's in very complicated ways, where these Graham positive things keep popping out as we, expand in some operad, and eventually it all straightens, and we're just happy at the end that all the coefficients are nice. If that could be done geometrically, I think that'd be very interesting.
Now, these are only n-dimensional subvarieties of the flag variety, is that right?
Yes, n minus 1 dimension.
So relatively small in a sense.
Yes, even worse, yes.
The biggest thing could easily be torus varieties. I guess.
I suspect that these ones literally are toric Bott-Samuelsons, or the small Bott-Samuelsons are toric, and I think
That's what
Yes, these are all iterated projectivizations of sums of two line bundles. We have proved that. Yes, this isn't like, oh, we haven't proved it because I said some lies. We proved it. It's in a paper that we haven't released yet, but I promise exists. Yes.
One more question. I may be just throwing a question that Vasu asked me back at you, but if that's the case, I'm sorry. But so what you described is you have this HHMP decomposition, n-1 factorial
Yes.
cells.
Mhm.
And there's this magical, like, and this simple idea of translating them all back to the origin magically collapses them into Catalan many cells.
Yeah.
Is there any shadow of the multiplicity left left over after you've done that?
That's a really interesting question. I don't think so. I think it really,
You just kill that information.
you just kill that information. Yeah. Yes. So it is also subtle because it's saying, for example, that the equivariant degree on the permutahedral variety is not technically what's computed when you compute the degrees on these cells. It's because when you translate by the torus, you also are messing with the t variables. So this formula that shows that these things expand Schubert positively, this is not like the fact that these coefficients are equivariantly positive is surprisingly not telling you that the equivariant degree on that the permutahedral Hessenberg variety is double gram Schubert gram positive. Yes.
Do you have some Poincare duals of the fundamental classes of your XFs?
That's a really good
flag variety.
That's a really good question. It doesn't look like it. One difficulty is that there aren't a lot of interesting. So it's a very, we did not find Poincare dual classes within the quasi-symmetric flag variety that would allow this to happen. Like it's not like there's some magic subvarieties. I think we might have ruled it out based on, there's like silly reasons why you need Poincare duality to give you a duality between the lowest dimension and the highest dimension. And somehow here we have a connected variety with like a bunch of top dimensional pieces. And that breaks most ways you would even try and get to it.
These are the full flag variety. I mean, these are some varieties of the full flag. So you want some classes that pair correctly.
Yeah, I recall that we weren't able to find any, it's not like we could find nice combinations of Schubert polynomials that restricted to forced polynomials on this flag variety. That I don't think that's possible.
There are probably more forced polynomials with a given degree than there are permutations, I guess. So you couldn't have a surjective pullback on cohomology, if that's true.
So there is a surjective pullback on cohomology.
There is a surjective.
Yes, it's the one that takes coinvariants to symmetric coinvariants to quasi-symmetric coinvariants. You just quotient by more things because you've imposed a less restrictive symmetry condition on the thing you're quotienting by. So you're quotienting more things.
So I guess you could then you could get some kind of dual kind of classes. You could look at the classes of those things.
I think that's possible.
Okay, let's